All right, so in the last video, we just looked at these formulas to find the center of mass of a plate or a two-dimensional object. So here we're going to just do a basic example. This one's coming straight from the book. The triangular plate shown in the picture has a constant density of delta is equal to 3 grams per centimeter squared. Then it's just asking us to find the moment about the y-axis, the total mass, and then whatever. I'm not going to do these things. I'm just going to go ahead and find the center of mass of the object, and finding the center of mass, we would end up finding all of this stuff anyway. So I'm going to copy this picture over to OneNote here. We have a triangle that goes from 0 to 1 on the x-axis and then up to the point 1, 2. And then it goes ahead and gives us these equations. I may or may not give you these, but they're easy enough to find. Okay, so let me go to a fresh page here and just copying down the picture. So this triangle goes to 1 and then up to the point here, 1, 2. It's a vertical line and then down to the origin. This equation was y equals 2x. This equation was just x equals 1. Okay, so if we want to find the center of mass of my object here, you first need to decide whether you're going to be doing horizontal slices or vertical slices. It doesn't matter which way you do it, the math works out regardless, but it may be easier to do one way or the other. This question is easy enough that we could do both. So I'm just going to do both just so we can get some extra practice in this so that you can see that they do come out to be the same thing. So let's first look at vertical slices. If I take my region here and break it down into these vertical slices, first off, right, these slices are going to exist between 0 and 1, and each individual slice is located at x on the x-axis. We would also need to know what the x wiggle, y wiggle is for each of the slices. That's the center of mass of the slice. So first things first, we're going to represent the mass of the slice as dm, and then we're going to need to come up with the x wiggle and the y wiggle. This is always what you want to do first for these questions. Decide whether you're going to do horizontal or vertical slices, then find the dm, the x wiggle, and the y wiggle. All right, the dm first. The dm represents the mass of each individual slice. It has the d out in front because it's a differential. Remember that these slices are supposed to be infinitesimally small. Like, they're not really even supposed to be a slice. There's an infinite number of them across the triangle here. Anytime you're talking about finding the mass of something, we're going to assume that this does have an area to it, so it is this rectangle. Finding the mass of something is just taking the density and multiplying that by the area. But because we have a rectangular area, the area is just length times width. Remember, it gave us the density in the problem. The density was a constant number 3. It is not always going to be constant. There may be x's or y's in it, but for us, just 3. Times the area of this rectangle, which is just going to be the length times the width here. The width is nothing, right? Because that width is that infinitesimally small distance. That's going to be the dx. But the length is going from 0 to the top of this diagonal line here, which is represented by the function 2x. So it's going to be the 3, the height or the length times 2x times that differential width there, dx. So just to simplify it down, this will be 6x dx. So this represents the mass of each of the slices as I move along the x-axis. Okay, the x wiggle is the x-coordinate of the center of mass of the slice. But because this slice is located at x, x wiggle is just going to be x for every single slice along my triangle here. Y wiggle, we have to be careful about. Y wiggle is going to be the halfway point of my slice. If my slice has a total height of 2x, then half of that is just x. So this is a coincidence. It's not always going to be this way, but here my x wiggle is x because we are located at x along the x-axis. My y wiggle is x because that is the halfway distance of my slice. Now that we have that, now we just go to the formulas. So there's going to be 3 separate integrals. These shouldn't be too bad. The first integral we're going to do is to find the total mass. The total mass is just the integral over, the integral over dm. So this is just integrate over, replacing dm with what we found dm to be, that's 6x dx. We're integrating from 0 to 1, since that's where my slices exist along the x-axis here. Pretty easy integral to do. Antiderivative here would be 3x squared, evaluated from 0 to 1, which is just going to give us a total mass of 3. So if you were to put this triangular plate on a scale, it would have a weight of 3 grams. Okay? We also need to find the moments. So let's find the moment about the y-axis. Does not matter what order you do this. The moment about the y-axis was the integral of x wiggle dm. So this is going to be the integral, still from 0 to 1, since we're integrating vertical slices along the x-axis here, of x wiggle, which was just x, times dm, which was the 6x dx. Alright, so this will be the integral from 0 to 1 of 6x squared dx, which has antiderivative of 2x cubed. That's from 0 to 1, so we just get 2. Alright, the moment about the x-axis would be the integral of y wiggle dm. Y wiggle was also x times that 6x dx for the dm. So that's the same exact integral that we just did up here, so it's still going to come out to be 2. Okay, and then finally, that means that we can find our x bar and our y bar, the actual center of mass of the triangle here. X bar we get by taking the moment about the y-axis and dividing that by the total mass. Remember, the moment about the y-axis came out to be 2, divided by the total mass 3. The y bar was the moment about the x-axis divided by the total mass. That was also 2 over the total mass 3. So that means that the ordered pair center mass of my triangle here, the ordered pair 2/3, 2/3. So just kind of looking at it on the graph here, remember that this had a height of 2 and a horizontal distance of 1. 2/3 is at about there, I guess, like 2/3 of the way. 2/3 here would be at about there, so I don't know, maybe there would be the center of mass. And it would balance there, so if you were to do like a 3D printer and print out this system and then stick your finger right there underneath the area, it would balance on your finger. Alright, so just real quick, we're also going to do horizontal slices. Okay, so with horizontal slices, it's going to look a little bit more complicated, and that's okay. Just know that it's still going to work out. So just to redraw the system over here, we still have our triangle from 1 to the point 1, 2, and then 1 on the x-axis, but this time with horizontal slices. Okay, if I am going to be making these horizontal slices, each one of these slices is going to be located at y on the y-axis. The center of mass of these slices is still going to be x wiggle, y wiggle. It's just that they're going to be defined differently than they were before. dm still is going to be the density times the area of each of my slices. The density is still 3 grams per squared centimeter. The area is this rectangle. Remember that this slice goes from the furthest distance x equals 1 to this distance here, which was represented by the equation y equals 2x. But because we're on the y-axis, I need this solved for y. So just to move it and solve it for the x to get the y on the other side, that's going to be x equals 1/2 y. Which means that the total length of my rectangle is going to be the furthest distance 1 minus that 1/2 y. That is the length times the width, which is going to be that infinitesimally small width dy. To try to simplify this down a little bit, we'll distribute the 3 into there. We're going to get 3 minus 3/2 y dy. Okay, so that represents the mass of each of the slices. X wiggle, we really need to be careful here, and you're going to see this a lot. X wiggle is the halfway distance of this slice. The halfway distance would just be the average of the furthest distance and the shortest distance. So we're going to find that halfway distance by adding these x values together and then dividing by 2. So we're going to take that 1/2 y plus the 1 all of that divided by 2 to find x wiggle. Simplifying this down a little bit, we get 1/4 y plus 1/2 when we divide each of those things by 2. The y wiggle, though, is pretty nice, luckily, because the y wiggle is the y coordinate of the center of mass, but if my slice is located at y as it moves up and down the y axis here, then that is going to be the y wiggle. Okay, now we do our integrals. So the total mass, and this had better come out to be 3, the total mass is just integrating over dm. Because we are integrating along the y-axis this time, my y-axis goes from 0 to 2 for this triangle. dm was this awful looking thing, 3 minus 3/2 y dy. Antiderivative here, the 3 goes to 3y. 3/2 y is going to go to negative 3/4 y squared. We're plugging in from 0 to 2. So if I plug 2 into this, 3 times 2 is 6. Minus plugging 2 into this one, 2 squared is 4, which cancels out with that 4, so we get 6 minus 3, which is 3. So yay, right, it did come out to be the right thing. Keeping it going, we're going to do the moment about the y-axis. The moment about the y-axis is the integral of x wiggle dm. Remember, this came out to be 2 before, and it still had better come out to be 2. This is going to be the integral, still from 0 to 2, of x wiggle, which was this awful looking thing, 1/4 y plus 1/2, times dm, which was this awful looking thing, 3 minus 3/2 y dy. Now maybe you can see why choosing the slices initially is very important, because sometimes the integrals come out to be kind of ugly. Not too bad though, we'll just FOIL these two things together. So the first, the 1/4 y times the 3 is 3/4 y. 1/4 y times the negative 3/2 y is negative 3/8 y squared. The 1/2 times the 3 is 3/2, and then the 1/2 and the negative 3/2 is negative 3/4 y. Kind of nice here because this positive 3/4 y and this negative 3/4 y just cancel each other out. So now it's the integral from 0 to 2 of negative 3/8 y squared plus 3/2 dy. Do the antiderivative. This is going to raise up to cubed and then divide by 3. So it's going to be negative 1/8 y cubed plus 3/2 y, that whole thing evaluated from 0 to 2. If I plug 2 into here, 2 cubed is 8, which cancels out with that 8, so we get negative 1. If I plug 2 into here, the 2's cancel, and we just get 3. If I plug 0 in, I get nothing. And then negative 1 plus 3 is positive 2. So yay, right? Math is amazing. We still need to do the moment about the x-axis. That would be the integral over y wiggle dm. I'm just going to do this one fast because this video is already getting kind of long. So this is still the integral from 0 to 2. Remember, y wiggle was just y, where my dm was that 3 minus 3/2 y dy. Distributing the y into there, we get 3y minus, this was 3/2, right? Yeah, 3/2, but now it's going to be y squared. Antiderivative, 3/2 y squared minus 1/2 y cubed. That's from 0 to 2. If I plug 2 into this one, I'm going to get 6. Minus if I plug 2 into this one, I'm going to get 4. 6 minus 4 really is 2. All right, and then you're going to do the ratios again, right? Now that we have the moments, the x bar is the moment about the y-axis over the total mass. The moment about the y-axis came out to be 2, divided by the total mass, which was 3. Y bar was the moment about the x-axis over the total mass, which was also the 2/3. So regardless if you do horizontal slices or vertical slices, you are going to get the same result. I'm going to make one more video of just a little bit more complicated of a question, and then if you guys struggle with the homeworks, of course, you can always ask questions during our meetings.